Hello dear students, let us continue with the topic oscillation. So in this class we'll discuss about simple pendulum and also we'll derive the expression for the time period of the simple pendulum. So you already know the meaning of simple pendulum. Simple pendulum means a string whose one end is attached to a rigid support and other end of the string is attached to a metallic sphere, and we will call that one as the bob of the pendulum, and this is a simple pendulum. And here the string, it is having the length L and M is the mass of the metallic sphere or bob. So if you drag the pendulum bob to one extreme position and if you leave, then what happens? Then the pendulum bob, it will starts to oscillate. So here we have dragged the pendulum bob to one of the extreme end. Then what happens? Then there will be formation of certain angle called theta. So here theta is the angle between the length of the string and this vertical line. So if the string is at the mean position, then theta value will be 0. So here actually there are two forces acting on this pendulum bob. When we drag the pendulum bob to one extreme end, then what happens? Then two forces are acting on this pendulum bob. So what are those? First one is tension. So this metallic bob, it has certain mass, right? Because of that mass, tension has created in this string along the length of the string towards the point of suspension, and that is the first force. First force is tension that has created along the length of the string towards the point of suspension. And second one is weight. So you already know that the earth has a gravitational force, and if you drop an object from a certain height, then that object will come towards the earth surface because earth has gravitational force. So because of the gravitational force of the earth, so the pendulum bob, so a kind of force is exerting on this pendulum bob, and that is what? Weight. So second force is weight of the pendulum bob that is acting in the downward direction. So these are the two forces, they are acting on the pendulum bob. So here actually, so when we drag the pendulum bob to one of the extreme end, so as I said, the weight is acting. So the weight, that force, that can be resolved into two components. The weight, that is mg, that can be resolved into two components. First one is mg cos theta, that is along the string, and second component is mg sin theta, that is acting perpendicular to the string. So these are the two components, and here mg cos theta is, that is the horizontal component. That is what? Mg cos theta. And here this horizontal component, that has balanced by the tension which has created in the string. So this horizontal component can be written as T equals mg cos theta, and I will name this one as equation number 1. And second component, that is the vertical component, that is mg sin theta, and this force is directed towards the mean position, and that tends to restore the pendulum bob to its mean position. Hence this force is called restoring force, and that can be written as F equals minus mg sin theta, and I will name this one as equation number 2. And according to the Newton's second law, we can write f equals ma, and I will name that one as equation number 3. And now if you observe equation 1 and 2, here LHS are same, so that we can equate the RHS terms. So from equation 2 and 3, I can write MA equals minus mg sin theta. So here cancels, so we left with A equals minus g sin theta. And here, as you know, theta is the angle between the length of the string and the vertical or mean position. So here, if theta is very small, so if the angle between the length of the string and that vertical, if that is very small, so that sin theta is nearly equal to theta, so that this equation becomes A equals minus g into theta. Now we can write the value of theta as, so we can write value of theta as theta equals x by L. We can write theta equals x by L, and we'll name this one as equation number 5. So here in the numerator x is there, x means x is the displacement of the bob. So when we drag the pendulum bob to one of the extreme end, it has certain displacement, that is x, and L is the length of the pendulum. Now I will put the theta value in equation number 4. Here is the equation 4. So this is equation 4. So in this equation I will put the value of theta. So if you put the value of theta in equation 4, so put the theta value in equation 4, then equation becomes A equals minus g by L into x. So we'll name this one as equation number 6. In this equation, A is called acceleration, g is the gravitational constant, L is the length of the string, and x is the displacement. Here g and L, these two are constant terms, so we can take g by L as constant, so that we can write this equation as A is directly proportional to minus x. So A is the acceleration produced in the object and x is the displacement, and here both are directly proportional to each other. And here a negative sign is there, that means the direction of the acceleration is opposite to the direction of its displacement. So in the last class we already discussed about simple harmonic motion. In that we have discussed the expression for velocity, acceleration. So for simple harmonic motion of the bob, the acceleration equation can be written as A equals minus omega square into x. So we'll name this one as equation number 7. Now compare equation 6 and 7. So here the LHS terms are same, so that we can equate the RHS terms. So from equation 6 and 7 we can write omega square, on both the sides negative sign is there, so that we can neglect the negative sign. So we can write omega square into x equals gx divided by L. Here x they cancels, so we left with omega can be written as omega equals, if square comes on this side it becomes square root, so that you can write square root of g by L. So this is the expression for the angular frequency, and from definition the angular frequency can be written as omega equals 2 pi by t. Now again here the LHS terms are same. If you compare equation 8 and 9, here LHS terms are same, so that we can equate the RHS terms. So from equations 8 and 9 we can write 2 pi by t equals square root of g by L. So now if you rearrange the terms, the expression for the time period can be written as t equals 2 pi into square root of L by G. So this is the expression for the time period of a simple pendulum. Now we'll discuss about damped simple harmonic motion. We already know that the motion of the simple pendulum swinging in the air, that will gradually, its speed will gradually decreases and finally it will comes to rest position. Why it will comes to rest position? This is because of the air drag or the friction at the support that opposes the motion of the pendulum, and gradually the energy of the pendulum will decreases and finally it will comes to rest position. Then we can say that the pendulum has damped. So based on the amplitude or displacement, the oscillations are classified into two types. One is undamped oscillation and another one is damped oscillation. First, we'll try to understand the meaning of undamped oscillation. For that, I will consider a simple pendulum. So this is the rigid support, this is the string, one end of the string is attached to the support, rigid support, other end of the string is attached to a metallic sphere, and we will call this one as the pendulum bob. Now if I apply the force on this pendulum bob, then what happens? It will starts to oscillate like this. So I will draw it separately. So on right side it will oscillate like this from this mean position. On left side also it will oscillate like this from the mean position. So let me say in the first oscillation it has covered the displacement 10 centimeter. So on LHS side also 10 centimeter. So during the first oscillation it has covered a displacement of 10 centimeter. In second oscillation again it has to cover 10 centimeter displacement on both the sides. And again in the third oscillation again it has to cover 10 centimeter displacement. So here what is happening? During each oscillation the pendulum bob, it is maintaining the same amplitude 10 centimeter, 10 centimeter, 10 centimeter. So here the energy of the pendulum, that is not varying, that is not decreasing, it is remaining constant. So that such oscillations are called undamped oscillations. That means if a system that oscillates with a constant amplitude forever, so here in each oscillation it is maintaining the 10 centimeter amplitude. So such oscillations are called undamped oscillations. And next we'll see damped oscillation. Damped oscillation means, so here if you take the pendulum and if you apply the force on this pendulum bob, in the first oscillation, let me say here is the mean position, from mean position towards right side it has to cover 10 centimeter, here also 10 centimeter. This is during first oscillation. In the second oscillation its displacement will reduces, that will decreases to 8 centimeter, here also 8 centimeter. Then in third oscillation again the displacement will decreases to 6 centimeter, here also 6 centimeter. Here what is happening? Here the amplitude of the pendulum, that is decreasing as the time passes. In the first oscillation it has covered 10 centimeter, in the second oscillation 8 centimeter, in the third oscillation 6 centimeter. Here as the time passes the amplitude of the pendulum, that is decreasing gradually. Such oscillations are called damped oscillations. That means if the system, if its amplitude decreases gradually with respect to time, such oscillations are called damped oscillations. So now if you represent these undamped oscillations as well as damped oscillations graphically, so here this is a graphical representation for the undamped oscillation. So here along y-axis we have taken the amplitude and along the x-axis we have taken the time. So during the in undamped oscillation, what happens? The amplitude that remains same in each oscillation, right? So here if you observe the crust height, it is up to here, trough height up to here. So this is for first oscillation. This is the graphical representation for the first oscillation. Then in the second oscillation, it has to maintain the same amplitude. So here also it is maintaining the same height, right? So here the amplitude that is remaining constant, right? Here the heights of the crust, trough, they are same in each oscillations. So this is undamped oscillation. In damped oscillations, again here along y-axis we have taken the amplitude and along x-axis we have taken the time. So in first oscillation the amplitude was high. In second oscillation what happens? The amplitude will gradually decreases, right? In the third oscillation again the amplitude will decreases still more. Then again it will decreases and finally that pendulum bob it will comes to rest position. So this is the graphical representation for the damped oscillation. And we can say that the damping force is directly proportional to velocity of the oscillator. Damping force means that is a force, opposing force, and that will causes opposition to the motion of the pendulum bob. The force which is causing opposition to the motion of the pendulum bob, that is what damping force, and that damping force is directly proportional to velocity of the oscillator. So mathematically we can write that one as F is directly proportional to V, and if you remove this proportionality we will get a constant term, that is B, so that we can write F equals minus B into V, where B is called damping constant. B is called damping constant. So this is about undamped oscillations and damped oscillations. So now we will see types of oscillations. So actually based on the frequency, the oscillations are classified into three types. They are free oscillations. First one is free oscillation, and second one is forced oscillation, and third one is resonance oscillation. Let us see one by one. First one is free oscillation. Free oscillation means a system that has to oscillate with its natural frequency without the help of external influence other than the impulse that initiated the motion. That means the object, it has to oscillate by itself with its natural frequency without the help of the external periodic force. So for example, if you take the tuning fork, and if you strike that one with the rubber pad and if you hold that one, then what happens? The prongs of the tuning fork, they will vibrate with their natural frequency without the help of the external influence. So that is the example for the free oscillation. And one more example, simple pendulum. So in simple pendulum, if you drag the bob of the pendulum to one of the extreme position and if you leave that one, then the pendulum bob, it will starts to oscillate by itself with its natural frequency without the help of any external force. You no need to apply the force continuously. Once if you drag and if you leave that one, then the pendulum bob, it will starts to oscillate by itself. So simple pendulum is also example for the free oscillation. So keep it in mind, free oscillation means a system that has to oscillate by itself with its natural frequency without the help of the external force. And second type of oscillation is forced oscillation. Forced oscillation means here the system that needs the help of the external force. So a system that oscillates with the help of the external periodic force with a frequency different from the natural frequency of the system. That means system that will oscillate only when we apply the external force on that one, and that system will oscillate with the frequency different from its natural frequency. Such oscillations are called forced oscillations. So if you take the example, if you take the tuning fork and if you strike that one to a rubber pad, then the prongs of the tuning fork, they will start to vibrate. And if you hold the stem of the tuning fork on a table, if you press the stem of the tuning fork on a table, then the frequency of the tuning fork, they are transferred to the particles of the table, so that the particles of the table, they will start to vibrate. So this is about the forced oscillation. So keep it in mind, in forced oscillation the system will oscillate only when we apply the external force on that one, and the frequency is different from its natural frequency. And third one is resonance oscillation. Here also the system needs the help of the external periodic force, so that a system that has to oscillate with the help of the external periodic force, and here that will oscillate with the frequency equal to the natural frequency of the system. So when we apply the external force on a system, then it will start to oscillate with the frequency, and that is equal to the natural frequency of the system. So these are the three types of oscillations: free oscillations, forced oscillations, and resonance oscillations. So with this I will complete the topic oscillation. Thank you.